Yeah, now in this session, so we here will be learning about the orthonormal, basically orthonormal basis and Gram-Smith procedure. So what we have done so far. So let me tell you first what we have done so far, and then maybe you will have sort of understanding why are we going to learn about these orthonormal bases and what are these orthonormal bases in together. So that I want to first set the context. So if you see first we saw what are bases, and then we saw how to make these bases orthogonal. Now I want to see what is this orthonormal basis, and from that I want to see what is an orthonormal matrix and how to convert a matrix, a normal matrix into other matrix which has these orthonormal columns basically. So let me first go on to this. So what is the definition of this orthonormal basis? So let's suppose we have the matrix A in which each column is independent. That will say that this is q1, this is q2, and this is q3, and so on. Let's suppose these all are independent and these are pivot columns. So we have the bases. So these bases are here q1, q2, q3, and so on till qn, let's suppose. Okay, so what is the meaning of orthogonality, if you know? So orthogonality says that if there are vectors, for example q1 and q2, they are perpendicular to each other. That's the meaning of orthogonal. That's what we saw about the orthogonality. Orthogonal. This is the meaning of that. This basically means if you take any vector qi and you sort of take its dot product with qj, where I is not equal to j, so this will give us 0 vector. This will be equal to 0 where I is not equal to j. This is meaning of the orthogonal. So what is the meaning of normal now? So normal basically means if this column is a unit vector. So what is the meaning of unit vector? That means, so if you multiply, if you take dot product with itself, so it will be equal to 1. Okay, and this is what I mean by, this is called orthogonal and this is called normal. So both of these properties together are called orthonormal. Is the definition clear? What is the meaning of orthonormal? So this basically means if we take qi transpose qj, this should be equal to, this is 0 in case I is not equal to j, and this is equal to 1 in case I is equal to j. That's the meaning of orthonormal. That's the first thing I want you to get this into the head. So if you have this property, and one vector will be, for example, like this, one vector will be like this, if we have some other vector it will be like this. Let's take the standard basis. If you see standard basis, let me show you the examples. So if you have in R3, we have standard basis 1 0 0, then we have 0 1 0 and 0 0 1. So these are three vectors. So if you see, this is vector 1, this is vector 2, this is vector 3. If you take dot product of this vector with this or this vector with this, you will get 0. But if you take its dot product with itself, so it will give 1. So these three form a set of orthonormal bases for R3. So that's why they are called standard bases. I told you something, they're called as standard bases. Standard bases. So in this, if you see the standard bases have some properties. What is the property? That they are orthonormal. Sometimes these are called orthogonal matrices. So if you see such a matrix, they're said as orthogonal matrix. So but I think name should have been orthonormal matrices. But if you see most of the books, they have written it orthogonal matrices. So but if you see in here, they basically are orthonormal matrices. You won't find this word with the matrices though. Okay, so what is so special about this? What is so special about these orthonormal or orthogonal matrices? So if you have a matrix A in which we have this q1, let's suppose, and we have this q2, and so on, and such that qi dot qj is equal to 0 if I is not equal to j, and is equal to 1 when I is equal to j. So if you have such a matrices, let's say this matrix with q. That's the standard symbol that you will use, that you will find in many books. So what is so special about these matrices? Why do we have to have a separate lecture on this? So the main thing that we can do is, if you see this q, so q transpose q basically is the identity. That's a property. This is the property that you should remember. These are beautiful matrices. So why? Let's first prove this. So q transpose basically means q1 transpose, q2 transpose, and so on. So then we have this. This is q transpose, and this is q. So this is q1, and this is q2. So if you now multiply these two things together, so this whole row, this row, will get multiplied to this column. So this will be q1 q transpose. So this will be the first entry. So this will be 1 because q1 transpose multiplied by q1 is 1. q1 multiplied by q2 is 0. Now everything will be 0 after 1. Okay, so everything will be 0. And for the second q2 q1, this q2 q1, so this will be 0. But q2 multiplied by q2, it will be 1 and then 0. Do you see that it will be identity? How many of you are able to see that it will be identity?
Yes, sir.
So this is the first property that they have. Okay, now coming to the projections. What is so special about this? If you see the projection matrix, in the projection matrix we have q q transpose q whole inverse q and then some b. Okay, and this is our projection matrix of this part. And then if you want to find that x hat, so what we do, we did this and perform the dot product. So if you now see that this q transpose q is this is identity, this much is identity, this is identity. So this projection now becomes q transpose, this is transpose here, so this becomes q transpose. This is the projection. Really simple. Are you able to follow this? Like how? So we want our matrices to be like this because our computation will become really simpler. So our projection matrix will become this. If you see the matrix that we had something A transpose A x hat is equal to A transpose B. Okay, and now you know that A transpose, this basically becomes identity in our case. So this x hat is directly equal to Q transpose B. If you want to find that, if you see the algorithm that we just went through, the linear regression algorithm, so in that we for example did this A transpose A whole inverse, then we performed a dot product with A, and then we performed the dot product with B in order to find this x. What if we had a matrix like this? In that the whole computation will get decreased. We don't have to perform this inverse, we don't have to perform this dot product, so we'll just do one. So we'll find this x bar is equal to Q transpose B directly with this. If but the condition is if this Q matrix basically was orthonormal matrix, orthonormal. But most the books will write it as orthogonal matrix. Okay, so it will be orthogonal matrix. So you saw that how much computations were we able to save? Are you able to see this? How much computations are we able to save?
Yes, sir.
So if we
Yes, sir.
have such matrices, and then I want my matrices to be orthogonal, normal, and one more thing, positive definite. I think that will take care separate in some separate lecture. It makes our computations and it makes our world in general very easy. So the first property that I told you about these orthogonal matrices was that Q transpose Q is equal to identity, and I proved that property like by just giving the multiplication proof. It's a simple proof. So the other thing is that if this Q transpose Q is identity, that means from this we can say that Q transpose is equal to Q inverse. Can you see this? Because that's the definition of this. If we have a matrix A and it's A inverse, so we say that it is equal to I. So this is called the inverse of A, or we write this A inverse of A is equal to I. So if something is written that Q transpose Q is equal to I, that means Q transpose is Q inverse. So if we have matrix Q, transpose of this matrix is its inverse. So this is the inverse. Are you able to follow this?
Yes, sir.
This is the first property, is that Q transpose Q identity. Then the second property I said from this property it follows from this property that Q transpose is equal to Q inverse. That's really simple. Now let me take an example. Let me take an example of permutation matrix. What is the meaning of permutation matrix? The permutation matrix is which will swap the rows. If you have seen the previous lectures, let's take a matrix 0 0 1 and then 1 0 0 and then 0 1 0. Okay, and this is the permutation matrix. And now I'm claiming that this matrix, this Q matrix, this is orthonormal or this is orthogonal matrix. Why? If you take any of this, because these three form the basis for this. Okay, so if you take any of these two, for example this with this with this, so you'll find that Qi transpose Qj is equal to 0 if I is not equal to j, is equal to 1 if I is equal to j. Take this matrix with this, so it will be 0. Take it with itself, so its dot product itself will be equal to 1. So I hope that you see that this is equal to, this is a orthogonal matrix or orthonormal. So Q transpose Q, if you see, it will be identity. Just multiply it with. So take the transpose of this matrix. And so I think it will be 1 0 0 0 1 0 0 0 1. This should be the answer for this. And again, some other examples. So some other examples can be cos theta. Let's suppose this is cos theta, this is sin theta, and we have minus sin theta cos theta. Okay, the first thing is multiply this with this. So this will be sine, if you multiply this vector with this, so this will be minus cos theta sin theta plus sin theta cos theta. This will get cancelled, it will be 0. So basically this vector multiplied with this is 0. But if you multiply it with themselves, so this will become cos square theta plus sin square theta. So you know that is equal to 1. And this again is a matrix. This is a matrix, and it also is a orthogonal matrix, or we call it orthonormal matrix. So again some other matrix, Q is equal to 1 1 1 minus 1. If you see this, you can form a lot of matrices from which you can get this. You can get the properties of orthogonal matrix, or we call them orthonormal matrices. Is it clear so far?
Yes, sir.
Yes, sir.
So these matrices we call them as orthonormal. Why are they special? I just showed you some properties of this. Okay. And now what I'll do is I'll go into this. I showed you the example of the projections. If you just want to see the projection, now I'll see if we have a matrix. So now I'll go into the meat of the lecture. That is the Gram-Schmidt procedure. So what Gram and Schmidt did? Gram, what the spelling? I don't know the name of the spelling. GRAM, I guess. Gram-Schmidt procedure. It's called. So if you have a matrix A, any matrix A, okay, and we want to make it as the orthogonal matrix or orthonormal matrix. So Gram-Schmidt basically they gave a procedure for that. That's why it's called Gram-Schmidt procedure. Why? Because you saw the applications that these orthogonal matrices have. So they have a lot of good properties, and it can ease out our computations. That's why we want to find a matrix A, and we want to find a matrix Q in correspondence to the matrix A, such that this Q is now orthogonal matrix or orthonormal matrix. Let me give you an example what Gram and Schmidt tried to did. So what they did, they said, for example, let's suppose we have this matrix in which the columns are A and B. Okay, we have a matrix in which the first is A and this is B, and let's say they are bases. They span some vector space. So now from this we want to get, this is our A, and we want to get Q such that we should have Q1 and Q2. And this matrix over here, it should be orthogonal or orthonormal. The columns should be orthogonal to each other, and the columns should be normal. So that's what they want. Okay, that's what they wanted. So what Gram did is he said Gram and Schmidt they gave a procedure for that. So what's the procedure that we'll see that now? What is the procedure? Then we'll take examples in order to clarify this procedure. The goal here is, this is our goal. This is our goal. If we have a matrix A in which these A and B are not orthogonal, if you see columns of that matrix, they're not orthogonal, they're not even normal. So what is the thing with that? So we have to do a lot of computations. But in order to get this good matrix Q, the orthogonal matrix, Gram-Schmidt they gave a procedure in which by using that we can get this matrix A into this matrix Q form. Okay, but the column space will remain same. Make sure, because column space should remain same. Column space should remain same. Okay, so why I said you this, the column space should remain same. That is, for example, if we have to solve this Ax is equal to B, okay, you have to solve this. So what I'm saying is that you try to get some matrix Q out of it. Okay, some other vectors, but it should span the same vectors. It should span the same vector space which is spanned by this Q. Then only we can find the solution to basically some Ax is equal to B. We'll find we'll find this. So we'll use this Q matrix now. Now you saw that Q matrix has really good properties, and it really makes our computation simple. The main point that you have to remember this: column space of A is equal to column space of Q. This should remain same. This should not get changed. And for that, but in the columns, this A and B. Now basically, what we want is something like this. Some orthonormal. They should be normal as with orthogonal. But the matrix, the column space of the matrix should remain the same. Solution should not get changed basically. Now what I'm saying, you one more thing, if we have this, before going to the procedure, I want again quote a property. If this Q is square matrix now, if this Q is like really good, if it's a square matrix, so for that we have this Q, and it's the square matrix. And what I'm saying you is that if you square it, you know that about projection matrix. What about the projection matrices? So you know that if you have projection, P square basically is again P. This is the thing that we learned. If you apply the projection twice, that basically gives you the projection back. That's the property that you learned from that. So if you have this, so we have this projection matrix now. Let's suppose we have this Q transpose. And if you multiply it again with itself, that's q transpose. Okay, it should give qt back. Now clearly you can see that this qt multiplied by q, this is the identity. That's the definition of orthonormal method. That's equal to qt. So this property is again the property that we wanted. This p square basically should be equal to p. Okay, now if we want to solve A transpose AX, this is the thing that we wanted to solve. A transpose B, this is what we wanted to solve if you see the linear regression. So now what we will do is we'll just convert this. We'll solve Q transpose Q X bar is equal to Q transpose B, because you know the column space will be similar. Now you know this is equal to identity. This is identity of X. This is equal to Q transpose B. The X vector is equal to Q transpose B. Only you will find this much. Okay, and now your linear regression again became less. So now if you are asked a question, can you reduce the complexity of linear regression? Yes, we can. So what we can basically, if we are given this matrix A, if we are given that matrix A, what we'll do, we'll convert that matrix into Q matrix. Maybe it'll take some time, it'll have some complexity. Okay, we'll convert that matrix into Q and then we'll reduce the computations, and you can just directly come up with the answers by using this QT by B. And now for that, you will have to have a procedure for that. You'll have to get this Q. And now we'll go to the procedure. Maybe in the assignments, I'll tell you to use the Gram-Smith procedure for the linear regression. It is not that you will just apply the linear regression that we taught. But what I'll do is, I'll be giving you a matrix A. I'll be giving basically data points. From that, you will create a matrix. And for the matrix, you will apply this Gram-Smith procedure so as to convert it into orthonormal matrix. And then you will just apply this operation. Now, what is the procedure for this? Now, let's take this 2 case first. So we had this vector A and we had this vector B. And now we need to convert it into, if you again see the setting of the problem, this was our A, this is our A over here. So this was non-orthogonal. I don't know whether they are orthogonal or not. And we have to find basically this Q such that Q1 and Q2 should be orthonormal to each other. And the column space of A should be equal to the column space of Q. Graham and Smith give the procedure for that. What is the procedure? Now let's go to the procedure. So what Graham and Smith said is, they said that, first let's see the Graham's part. I don't know what Smith has done. Let's see the Graham's part, what Graham did. So he said that this, we want, let's suppose Q1 and Q2 out of this. We want two vectors such that they should be orthonormal. He said A is equal to Q1. Let's put this A is equal to Q1. Let's put it equal. So this basically is the Q1. And now he said, instead of this B, you should get the other vector. Instead of this B, you should get the other vector. So for that, what you should do is, this basically B, it should be one is this vector. If you see, one is this vector. The other vector, he said, should be perpendicular. So it should be like this. If you now see that the B has the projection onto this vector and B has the projection onto this vector. Now this A is taken. Okay, he said, just take out this part, take out the component that is perpendicular to this and remove the component that is onto this. So B basically is A, whatever A is. Whatever B is basically B, and remove the component, remove this component basically, remove this component which is on A. So you'll be left with the component that's perpendicular to this. Again, let's come up again. This is A, this was our B. So what am I saying is, this B has basically two components. If you see the projection, so this is the projection onto A, then this is the projection perpendicular to A. There are two projections onto this. So what Graham said that this A, let's take it Q1. Let's say this is Q1. For the second vector, what we'll do is take this B and remove this component which is along this A. So we'll be left with only this component, That component is perpendicular to A. If you again see the null space of the picture, so in that, this B's component which lies in this A, which lies in the column space of A, like take that out. If you take that out, then we're just remained with the perpendicular thing. We are remained with the vector that lies basically in the null space of A transpose. This basically lies in the null space of A transpose now. Okay, that vector we will take, this vector we'll take, and we'll remove this vector. So B minus, remove the projection of B onto A. This should be removed. But you know the equation. You know what's the projection of B onto A. That we have seen that projection matrix. So what to do now? So that is, if we have this vector B minus something A, because that is along this A. Okay, and what should be what is that? That is A transpose B divided by A transpose A, that we have seen from the projection. Is the Gram-Smith procedure for two vectors clear at least? Is it clear for two vectors? What he said is, if we have, let's suppose, two vectors A and B. So A vector, let's take it as it is. Let's say this is Q1. If you want to find a vector for which you don't have to, the column space should remain the same. So what he said is, this B vector basically has two components. One component is along this A and one is perpendicular to the A. So you have to do one thing. Instead of taking this B, take this component of B. Take this component of B. So how will take this component of B? So B minus the component which is along the a-axis. The component which is along the a-axis is basically projection of B onto A. This will be R new. This should be not, this is not B, this is basically Q2. Sorry, this is Q2. This will be R Q2. So if you see, this is Q2, this is equal to B minus, so this was our projection matrix. That's the x bar. So it was A transpose B divided by A transpose A, and then multiplied with A. This is our Q2, and Q1 basically is directly our A. So these are our, now we had this A in which we had A and B. Is that what we had? Yes, we had this A and B. Now we converted into Q, in which we have Q1 and Q2. Is it clear?
Sir.
Is the
Yes,
procedure
sir.
clear for at least the matrices in which we have the two columns in which the basis is 2?
Yes, sir.
Okay, now you can say these are orthogonal. What is the, I think this is the Schmidt's part. Now Schmidt's part comes in. Now you have to normalize it. In order to normalize it, you know how to normalize. You'll just take the norm of this Q1. You'll just divide it. This Q1 divided by norm of Q1. In order to make it unity. Q2, norm of Q2. So that was the Schmidt's part. This is normalization. You're just normalizing it. If we have a vector, for example, 1 0 2, and if you want to find a unit vector out of it, what you do is 1 square plus 0 square plus 2 under root, that is equal to under root of 5. So you divide by, it's 1 by under root 5, 0, 2 by under root 5. So this vector is a unit vector now. So if this was vector A, so what we write is A is equal to A divided by norm of A. Normalize it basically. So in the similar fashion, this vector is still not normalized. Maybe in order to get this Q1, this A divided by A normalize, and divide by this Q2 normalize now. Okay, the first part is that we'll get vectors. The first part is Graham's part. Let's call this Graham. I don't know who discovered it. So the thing is, the first part is we'll find this. Let's call them A comma B. So from small a comma B, so we'll find this AB. This is one part. The second part is normalization. So in normalization, what we do is we'll write Q1 is basically equal to A divided by norm of A, and Q2 is equal to A B divided by norm of B. This is normalization. I did not want to make the equations look like tedious and stuff. So that's why normalization. I showed it in the two-step process. Is this clear? Let's take an example. Let's take an example. Let's suppose we have this. What example should I take? I'll take some easy example so that, let's suppose we have this 1 1 1. The matrix that we had earlier. Let's take that. Then this is 1 2 3. I think this was the one. This was 1 2 and 3. This was 1 2 3 1 2 and 3. Let's make it simple. 1 2 3. Okay, as you clearly see that this is, let's suppose, A, and this is not orthonormal. In order to make this orthonormal, so what I'll say is, I'll say this is our A directly, this is our A, and we have to sort of find the norm of A. So that is, I think, root 3. That is root 3, and you will get this A. Now this Q1 basically is equal to 1 divided by root 3, 1 divided by root 3, 1 divided by root 3. That's Q1. In order to get this Q2, so first we'll get B. So what we'll do is, we'll get this 1 2 3, that is this portion. In order to get the capital B, we'll take the small b, and then minus something multiplied by A, the whole matrix A. And we'll, what is that something? That something is this much. That something is the projection along to that. The projection we have written is A transpose B. A transpose B divided by, I think I have written it, divided by A transpose A. Divided by A transpose A. you compute this value, okay, and subtract that from this value, okay, then you will get some value. Let's suppose we got a1, a2. I don't want to make computations. A3, something like this. And then you'll normalize it. You will say q2 is equal to b and then norm of b. This will be our q1 and q2. Is it clear? Is the procedure clear?
Sir.
Okay. Now we have to generalize it. Let's suppose we have q1, q2, qn who have a matrix A in which we have, let's suppose, a1, a2 till an, something like this, and we want to convert into q. We want to convert it into q such that these columns in here are orthonormal. So what should we do? The first thing is the step one. If you write step one is take this a1 as it is. Take this a1 as it is. And then what should you, the second part parallelly you should do is, in order to find this q1 is equal to a1 divided by norm of a1. This is the q1. If you now want to find this q2, what you will do is you will first find that q2 like this. That will be, take this q2 and subtract this component along this a1. Okay, subtract its component along this a1. So how to do that? Just see the projection. Just see its projection. The projection will be a transpose. Okay, then let's suppose that is some vector. If we have ABCs, let's suppose this is a transpose divided by a transpose a, and we have to remove its component along this wise, and we'll write it a transpose a, and let's write this is a1. You'll have to remove that component along the a1. Okay, and then if you want to find this q2 now, and what this q2 is, small q2 will basically be equal to, take this bigger q2 and find its norm in order to make it unit vector. So for the q3 now, in order to find this q3, what you should do in order to find from this a3, the a3 that we have, from this a3 you should remove its component along this. This was our a and we called it q1, so it should be along q1. Basically this should be along q1 instead of this a. Okay, and then what we have is, we should remove the component that it had along this q3, had this a3 basically had component along a1 and it had component along a2 as well. So remove those components. So minus, remove the component and remove the component, and you are here, they will be projection matrices. It will be projections. And similarly for the qn, what you should do is take this an, from this take this an and remove the components along the a1, along the a2, along a n minus 1, and remove all these components. Okay, remove components along a1, then remove components along a2, and at the end remove component along the an. And you know what is the factor here? The factor here is basically projection over here, so these are projection matrices. And at the end what you have to do, you have to normalize it. Whatever you get for example q1, you get q2, and so on till qn. But these are sort of orthogonal, but they are not normal now. So in order to make this normal, you will just divide it by q1. You will just divide this by q2, divide this qn, and now the matrix you will get, let's suppose this we call as q1, this will cause as q2, small q1, q2, and qn. So this will be q. Now the matrix q will be q1, q2, and so on qn. This is the procedure. Again, let me just summarize the procedure. The procedure basically is, if you have a matrix in which the columns of that matrix are not orthogonal and normal, so in order to make it an orthogonal matrix, Gram-Smith gave a procedure. They said what should we do is, we'll take the first column as it is and just normalize it. In the second column, we'll remove the component of the first column. In the third column, we'll remove the component of the first and second column, and then normalize all the things together. That's the stepwise procedure. In order to write this procedure now, procedure basically is the step one: take first column as it is, just normalize it, just normalize in order to make it unit vector. The step two, or we can say while loop over here. So while there is a column, where there is a column, because this is the iterative process. Now take that vector. So take, let's suppose ai, okay, and remove components along ai minus 1. So that means, like, for example, if you take A3, remove A2 component, remove A1 component. If you take A11, remove component along A10, A9, A8 until A1. Remove all the components that we have along the other axes. So that's how it should. And at the end, you should normalize everything. Normalize. This is sort of a three-step process. The step one, and this, there are multiple steps involved. The step one is take the first column, make it, and take it as it is, and just normalize, and this will be your Q1. And then from this process, you will get you'll get this bigger Q2, Q3, and then when you normalize, you'll get this smaller Q1, Q2, and so on. From here, you will get smaller Q2, Q3, and Qn. And now, when you put this Q together, it will be like this: Q1, Q2, Q3, and so on. I hope the procedure of Gram-Smith is clear. Is it clear?
Yes, sir.
But speaking like realistically, the common, for example, if you see, if you want to make this A into this Q matrix, the packages, like, for example, if you have MATLAB, LaPack, and package, they don't use the Gram-Smith procedure. They use something called as householder's reflection. Householder's reflection. This is the algorithm they use basically. But here you saw how to use the Gram-Smith procedure. I think you will be able to sort of come up with now make this write a code for this and make any matrix A into an orthonormal matrix or orthogonal matrix. Is it clear? I think
Yes,
if you
sir.
have questions, I'll just stop here. I'll stop the recording here. I'll take your questions, and I have to discuss some things with you.